All right, so chapter 8 is the short chapter that we're going to start today, and it's all on polar coordinates and polar graphs. And I like this chapter because it's a nice switch, because all of the math that you've learned up to this point has been in Cartesian, in the world of Cartesian points, coordinates, and graphs. So if you look at this right here, which is not in your notes, but just to give you a visual of what we've been doing and how we're going to use what we know to go into this new world of polar graphs, we have what we're used to, which is the Cartesian graph. So we've got our y-axis, our x-axis, and we talk about points in terms of their x-coordinate and their y-coordinate. So now I'm going to show a polar graph. So when we look at this, it's very different than what we're used to, but it's still a plane that we can represent points in. But instead of x's and y's, we use r's and thetas. So r being the radius, or how far away from the pole, and the angle at which you've been rotated from the polar axis. So I'll go over what those two things are in a second. The cool thing about the Cartesian graph and a polar graph, you can represent the same point in space using either one. So this is kind of hard to look at, but if you think about where on the Cartesian graph, let me switch to where the x-axis and y-axis would be, I can represent the point 3, 2 here using x's and y's, but I can also represent that as some distance from the pole, which is what we're used to calling the origin. So that distance would be r, and some angle of rotation from the polar axis, which we're used to calling the x-axis. So the neat thing is we can go back and forth from one to the other. You can represent the same point in space using x's and y's or r's and thetas, and we'll be able to go back and forth between the two. The reason we have polar coordinates and polar graphs is because some graphs just make more sense to use a polar equation because of how complicated and messy it would be in rectangular form, which would be the Cartesian graph. So let's go ahead and okay, so a couple of quick examples of places that you guys have already seen polar graphs, but maybe just didn't know that's what they were called. Right here we're looking at a screenshot of some radar, weather radar mapping, apparently a Canadian one. But you guys have seen this before, and the reason that weather people use polar is because there are weather towers located in different spots of land, and each of those towers can map out the radar for some specific radius. So that's why they use a circular or polar graph for how far out a specific weather tower can reach. Here we see another, I don't know what this is from, probably a video game. These are images I got just from Googling real world examples of polar graphs. So I'm not exactly sure if this is a real one. It looks like this is representing movement of these arrows, something, maybe aircraft or something. Here's another one. This one looks more like an actual airplane or some sort of aircraft. Okay. All right, so let's get into the notes now. And we're going to start by defining just the most basic parts of the polar coordinate system. So to go over specific definitions, and I kind of mentioned these when showing you earlier, when we're looking at the polar coordinate system, what we're used to calling the origin is called the pole. And then what we're used to calling the x-axis, since we're no longer in the world of x's and y's, this is called the polar axis. And all of the points in the polar coordinate system are assigned by coordinates, and those are r's and theta. So we were used to using x and y's, we use r and theta. You'll also notice that rather than the parentheses right here, we also use brackets to indicate just that we've made the switch to polar. So you'll notice that as well. So again, r itself represents the distance from the pole. So how far a point in space is away from the actual pole. So r is the distance from the pole. And theta is the angle of rotation from the polar axis. So if we're thinking of this being 0 degrees, which makes sense when we think about our unit circle, and I want to open up to, let's say I want to plot this point right here, then theta would be whatever angle is formed to open up to get to that point, which in this case it looks like it would be about 60 degrees. So theta is the angle of rotation from the polar axis. And to give you some frame of reference of what we're looking at compared to what you're already familiar with, let's think back to our unit circle. So our unit circle, we had 0, 0, and we always thought of this in terms of x's and y's because that's what we're used to using, that's what we are used to working with. And in each of these points around the outside of this, especially the ones that you memorized as on the unit circle, every single one of those, because it's called the unit circle, it has a radius of 1 unit away from the pole. So if you think about that, back to this example here, the unit circle that I'm going over with green, that's where we've been looking at in terms of this polar graph. Now we're just going to expand that and go further. We don't have to always have a radius of 1, but theta still represents that angle of rotation, and then r can be anything. We can go any distance away from the pole. So we're just expanding our window of the unit circle when we look at a polar graph. So let's plot some points on it. And let's see, we've got the point -4, 2 pi thirds. So -4, no, it doesn't make sense to have a negative value for a radius if we're thinking about a physical object. However, just like you can go left and right in polar coordinates and up and down for positive and negative values of x and y, we can also think about r and theta in that same way as well. So let me get a better view here. So we're going to graph -4, 2 pi thirds. There's a couple of different ways you can think about this. I always like to describe it as pretend you're standing right here at the pole facing the direction of 0 degrees. So if you're standing right in the center of that, facing 0 degrees, when you open up to a radius of 2 pi thirds, so here we see 2 pi thirds, and if I'm opening up, let me switch to green, to that, then imagine facing 2 pi thirds. So that's the angle, that's our theta. So we've opened up to face that. But because our radius is negative, as we're facing 2 pi thirds, imagine walking backwards 4 units. So that accounts for the negative value of r. So you would go backwards 1, 2, 3, 4, and that would be the point A. Okay, so now let's plot one with a positive radius, but with a negative value of theta. So just like you guys already understand negative rotations, negative pi halves would be the opposite direction of positive pi half. So that negative rotation means we're actually just, if we're facing the 0 degree direction, we're just going to turn towards the right in the negative direction here. So if we travel or rotate to the negative pi halves direction, we'll be facing 3 pi halves. And then because r is positive, we will imagine again we're facing negative pi halves. Then you would walk forward to represent that positive value of r 3 units, and we would land right here at the coordinate 3 negative pi halves, or b. And then for this last one here, we're going to rotate 150 degrees. So if you think about pi being 180, 150 is this one, 30 degrees right ahead of it. So we're the value of theta, we're opening up in the positive direction of 150. So imagine again starting facing the 0 degree direction, rotating your body, and now facing 150 degrees, or 5 pi over 6. But this negative value of r means that now we're walking backwards 2 units. So this first inner circle would be -1, and then the second one right here in this pink color we see -2. So that would represent point C, which is -2, 150 degrees. So now we're going to look at ways to represent the same points that we see, those 3 points, with different values of r or theta. So you can represent the same space polar point using different values of r and theta. And what I mean by that is, for example, we'll just jump into here with A. So if I want to represent the point A, which was green on our polar graph, I can get to that same location on the polar coordinate system by just maybe changing one thing about r or theta. So this problem is saying now I want you to use a positive value of r to represent A. So if you think about starting at the origin or at the polar axis facing the 0 degree direction, and if I want to walk towards or forward to get to my point A, then I need to represent either rotating all the way out to that or going in the negative direction of theta. So changing my value of r for point A to a +4 means I also need to change the theta. So I either want to open up the positive 5 pi thirds or do a negative rotation, and both of those would be considered correct because you would still get to the exact same point. So if I do use a +4, that means instead of rotating 2 pi thirds and going backwards like we did originally, we'll open up all the way to 5 pi thirds and then walk forward. So we could also say we could have a positive value of 4, meaning walking towards A, if I just do this negative rotation, and that would be the same as pi thirds of that rotation, but just in the negative direction. So +4, negative pi thirds. So all 3 of these polar coordinates, so this one, the -4, 2 pi thirds, 4, 5 pi thirds, and 4 negative pi thirds, all represent this exact same spot or that same location on a polar graph. So if we look at point C now, when we want to represent that same point, so that's in the pink color, that one originally had a radius of -2. So we want to represent that same location with a +2 radius. That means we're going to either open up, instead of, we stopped at 150 degrees originally and walked backwards. So we could rotate all the way out to 11 pi over 6 and walk forward with that for that +2r, or we could just make this tiny rotation in the negative direction. So both of those would be considered correct. So you could open up all the way to 11 pi over 6, or that would be 330 if we're going to stick with degrees. Or you can have a negative rotation and then go in the positive direction too as well. So all three of those coordinates represent the same exact point on the polar graph. So that's not something we were able to do on a Cartesian graph. X's and Y's, you couldn't represent each coordinate in a Cartesian graph with different options for X and Y. So that is a unique characteristic of polar graphs. Okay, so now I want you to get a little practice doing this now that you've seen me talk through some examples. So in example 2, plot the following points. If you look at example or point A, which is 0, 360 degrees, think about what a radius of 0 is regardless of the rotation. So for this, no matter what the rotation is, with a radius of 0, your point is simply located at the pole. So that would be point A. So point B, we have a radius of 1 and a value of theta of 7 pi over 6. So again, for part B, let me switch colors here. For B, which I'll do in pink, imagine standing at the pole facing the 0 degree direction. When we rotate to 7 pi over 6, now we're facing that rotation, and because the radius is positive 1, you move forward 1 unit in that direction. So that would be point B. And then point C, we're going to move in the negative direction, or with a negative radius of -3, and our rotation is 5 pi thirds. So that means we would open up all the way to 5 pi thirds. So imagine facing 5 pi thirds right here, but because r is negative, you would move backwards 3 units, which would put you right here. That's where C would be. So we can represent each of these using different coordinates as well. So for A, obviously, r is going to be 0 regardless, and any rotation would be fine. You could have a rotation of 23 degrees, you could have a rotation of -4 degrees, it doesn't matter. So you'd always land at the pole with a radius of 0. Part B, let's say we want to represent our point B using a negative radius. So originally with B, we opened up 7 pi over 6, which is right here. Well, if I want to get it to my point by walking backwards or moving in the negative direction 1, that means I would need to be facing what's directly opposite of that, which would be pi over 6. So by facing pi over 6, then I could walk backwards 1 unit, which would get me to point B. So that could be one of the different options to represent that same exact point. And then for C, let's say we want to use a positive value of r. Then instead of opening up 5 pi thirds and walking backwards, imagine opening up to face 2 pi thirds, what's exactly opposite of that, and then you would move forward 3 units. So this is just how to plot or rewrite coordinates on a polar graph. And eventually we'll start looking at entire polar equations to represent not just a single point, but actual curves in graphs. So that is what we'll be doing in a little bit. So you remember from the intro of this video where you saw the Cartesian grid over top of a polar graph? We have the ability to go back and forth between x's and y's to r's and theta. So we can represent the same point in that 2D space using either one of those. And so on this page, we're looking at how exactly to convert from one to the other. And you guys already have a base of knowledge about how to do this. So we'll look more closely at exactly how and why we'll use the formulas that we do. Okay, so we're going to start with considering a point. Now, what I'm drawing right now I'm trying to relate this to what we already know about x's and y's. So if I outline my Cartesian axes, and then let's say I want to plot a point right here in between, right in the middle of that first quadrant, what we're used to calling quadrant 1. So if I'm plotting a point here in Cartesian world, I would represent that single point with the coordinate x, y, depending on what x and y were right there. I can talk about that exact same location using r and theta, and we're going to see how to go from one to the other. So the first thing we're going to do right here is going from polar to rectangular. So that means given the radius and the rotation, what is that xy coordinate? So what are x and y if I already know what r and theta are? So if we're thinking about this in terms of r and theta, that means my value of r starting from the pole going out to that point, that's what r represents. And theta represents whatever rotation got me from this polar axis to that direction where you move forward r to get to that point. So if we know those two things, how can we get to our x's and y's? So if you think about this back to in terms of x's and y's, if my x coordinate represents some distance on the x-axis, then I know that this distance here is x and my vertical distance is y. So we know that just from our basic knowledge of a Cartesian plane. And if I want to relate r and theta to x and y, as you can see here, we're going to use the cosine and sine function, because what we have now when we actually draw a physical representation of our horizontal distance x and our vertical distance y, we have a right triangle, and there's lots of right triangle ratios that will help us. So the cosine of theta will help us relate x to r. So cosine is adjacent over hypotenuse. So the cosine of theta, by definition of cosine, is x divided by r, which means if I want to solve for x alone in terms of r and theta, I would just multiply both sides of that equation by r, and that would get us with this equation, x equals r times the cosine of theta. That should seem a little familiar to you, because as we were using our unit circles, we always reviewed and stated over and over that x is the cosine of theta and y is the sine of theta. And this is why, this right triangle is why we use that knowledge. So the only change here is that we're not looking at a unit circle. Our value of r, or the radius, can be any number. So typically we said x equaled cosine theta. But our r that we were using was always 1. So it's actually r times the cosine of theta. And then we can see the same thing happen here with sine. So the sine of theta would be the opposite over the hypotenuse, which is y over r. And then to solve for y, you would just multiply both sides by r. So y, we would calculate that by multiplying the radius times the sine of theta. So that's how we would quickly convert from r's and thetas to x's and y's. So these relationships right here are very important. You will rely on them a lot in this unit. So now we're going to see how to go from rectangular form, which would be given x's and y's, how do you determine what the values of r and theta are going to be. So those aren't quite as intuitive because we've kind of used the other direction already. And this one, you'll see it's outlined for you of how we're going to do that. So if we think about this right triangle that we formed on the polar graph, we do have some ways to relate these two things. So if we're talking about tangent of theta, that's the opposite side over the adjacent side. That's a quick way to get directly from knowing theta to knowing y, and x, because the tangent of theta is always going to be y divided by x. Which means if I want to know what theta itself is, all I would have to do is apply the inverse tangent function to both sides of that, and that would give me the value of theta itself. So theta is always going to equal the inverse tangent function of y divided by x. And again, the reason we know that is simply because based on this visual right here and what we already know about right triangle trig, whatever rotation that is, it will get us the value y divided by x when we apply the tangent function. Okay, and then to figure out the value of the radius, we already, again, looking at this right triangle, we know the Pythagorean theorem, which says x squared plus y squared. What we're used to saying is a squared plus b squared equals c squared. So the values here would just switch to x squared plus y squared equals r squared, which means if we want to solve for r, we would just take the square root of both sides, and we would solve for r, which would be the positive or negative square root of x squared plus y squared. The reason we'll have two options here with the radius, positive or negative, is kind of how we saw on the last page. You can represent the exact same point on a polar graph in more than one way. So there's not always a right answer here with positive or negative. I typically revert to positive and then think about theta based on that. But there's more than one way to represent the same exact point here. So that's why you do have to consider the positive or negative option for r. Okay, so these are the formulas used for getting from polar to rectangular coordinates or from rectangular to polar. And we were able to visually see all of those relationships simply by looking at a right triangle that's on both the Cartesian and the polar graph of this. So these are functions or relationships that you'll need to know moving forward and need to be able to remember on your own. But just remember that you can build all of these simply by drawing a right triangle, but on an overlapping polar graph and Cartesian graph. Okay, so now let's look at applying those formulas. So we are going to find the rectangular coordinates for a couple of polar points. So that means we're starting with r and theta, and we're going to convert to x and y. So we're looking at a value of -2 for the radius and a rotation of pi for theta. So when we want to switch that to x and y, think about what our formula said. X equals r times the cosine of theta. So this would simply be -2 times the cosine of pi. And from our unit circle, we know the cosine of pi is -1, meaning the x value at pi on the unit circle. So -2 times -1, this just means x equals 2. And y equals r times the sine of theta. And the sine at pi, think about that y coordinate on the unit circle with a rotation of pi. You're not moving up and down anything, so that would just be -2 times 0, which is 0. So this polar point of -2 pi is the same rectangular point 2, 0. And that should make sense. So if you're thinking about where that is, I'm just going to do a quick sketch up here. The rotation of pi, here's pi, on a polar graph, and then so imagine opening up and you're facing this direction now, and then you move backwards 2 units, you're going to land right here. So that's clearly the point 2, 0 in rectangular form. All right, so now let's jump over to part C. So we have got the polar coordinate 5 negative pi fourths. So it's given to us in the form of r and theta. So to find x and y, we simply apply the formulas that we derived above. So x would be r times the cosine of theta, negative pi over 4. Using your unit circle, which you should always have handy at this point when we're talking about polar graphs. The cosine of negative pi over 4. Think about where positive pi over 4 is, and then you would identify where negative pi over 4 is. The cosine would be the x-coordinate for that, which is root 2 over 2. So the x value here is just 5 root 2 over 2. And then to find the y value, we would apply 5 times the sine of theta, which is actually the sine of negative pi over 4 is negative root 2 over 2. And you should know that by looking at a unit circle. So this polar coordinate in rectangular form is 5 root 2 over 2, comma, negative 5 root 2 over 2. All right, so now we will go in the opposite direction where we're given rectangular coordinates in terms of x's and y's, and now we're going to convert those to polar coordinates of r and theta. So we're given x and y here in example 4. I'm going to just start with part B. Part A, the point 4, 0, think about where that is. If we've gone over 4, up 0, on the polar graph of that, that's still a radius of 4. We've moved out 4, and we haven't rotated any, so you're still in the 0 degree direction. So those, you can kind of reason your way through the polar representation of that, which would be a radius of 4 and a 0 degree rotation. You can still apply the formulas and you'll end up with those same values. You could also do a radius of negative 4. And if I have a radius of negative 4, that would mean I'm facing this direction and walking backwards 4 units. So that would mean we have to open up to either 180 degrees or pi radians for that. So those are two representations of the 0.40. But I wanted to look at some examples using the actual formula. So if we look at B, we're given x is 5 and y is negative 12. So referencing our formulas up above, if I want to calculate theta, then I would apply the inverse tangent function to y divided by x. So negative 12 over 5. So this is just calculator punching. So one thing you have to be careful of, though, is if you want to represent your theta in terms of degrees versus radians, you need to make sure you're in the right mode. So because visually degrees makes more sense to us when we're thinking about just real world angle measures, I would suggest sticking to degrees when you're going from rectangular to polar. So on your calculator, you would just type in inverse tangent of negative 12 fifths, and your calculator should punch out negative 67.4. So think about what that rotation looks like if we're on a polar axis. With a rotation of negative 67.4, you're going in the negative direction. That should make sense. So think about where this coordinate is, 5, negative 12. So just visualize where that is in a rectangular graph. That's quadrant 4. So a rotation of negative 67.4 makes sense. So it should make sense. There will be times where that value you get from the inverse tangent function doesn't make sense. And that's because when you calculate inverse tangent of a number, you're given a reference angle, which means it is the angle of rotation from the polar axis. It could be from 0 or it could be from 180. So that's something you have to think about every single time you calculate theta using inverse tangent. So for us, that makes sense because we know our coordinate is in quadrant 4, so a negative rotation of 67.4 makes sense. So for the value of r, we know that's going to be the positive or negative value of x squared plus y squared. So that's 25 plus 144, which is the positive or negative square root of 169, which is the positive or negative radius of 13. So again, we can represent this same point using multiple different coordinates. It just depends on what's going to match with our negative value of theta. So if I'm rotating a negative value of theta, now I'm facing that coordinate, then I would want a positive value of r because I'm going to move forward 13. So this polar coordinate is a value of positive radius 13, and the rotation was negative 67.4 degrees. All right, for this last example, part C, we want to find the matching polar coordinates for the rectangular coordinates negative 2, 3. Again, we have the formulas, and theta can be calculated by taking the inverse tangent of y over x, which is inverse tangent of 3 over negative 2. If you punch that into your calculator, inverse tangent of 3 over negative 2, you get negative 56.3 degrees. You should stop and think about where that is based on where this is. We have a quick way to reference visually where negative 2, 3 is. We know negative 2, 3 is over here in quadrant 2. So think about a rotation of negative 56.3 degrees. That does not make sense based on visually where we know negative 2, 3 is. And again, anytime you calculate an angle using inverse tangent, you are actually calculating what we call a reference angle, which is an angle from the polar axis, either from 0 degrees or from 180 degrees. So with this one, we can use a negative rotation, but that means we would have to choose the negative value of r as well, because if I rotate negative 56.3 degrees, I'm facing away from the coordinate that I want to represent. So once we calculate r, we would just have to make sure we either choose the negative value, or before we do that, go ahead and just add 180 to this 56.3 or negative 56.3, and that would give us 123, which would be the actual positive value of theta. So I'm going to do that. I'm going to stick with that positive value of theta by adding 180 to the negative 56.3, and you get 123.7 degrees. So then when I calculate r, I'll just use the positive value since I'm going in a positive rotation, and then I'll walk towards that coordinate that I want to represent. So r equals the positive or negative, but I'm going to go with the positive, square root of negative 2 squared plus 3 squared. So we've got the positive square root of 13, which you can just leave as the root. So if we want to just represent exact value of r, we would keep it as the square root of 13. So this coordinate, negative 2, 3, we can represent using a polar coordinates of the square root of 13, comma, 123.7 degrees. We could also have used a negative value of r as long as it makes sense to get to that point. That would mean we would use our negative 56.3 degrees. So you've seen how to convert from rectangular to polar, polar to rectangular, using these formulas that we sort of derived and saw how they make sense. So again, just to reiterate, these relationships you will need to know on your own. So the more you use them and apply them, the faster you'll be able to recall them. But if you ever get stuck, draw a picture of what you know, and you can get to these very easily. So I'm going to stop here and pick up with 8.3 in class next time.